Hey there, in this video we are going to talk about inverse functions. Now the concept of an inverse is something that you probably are familiar with even if you're not familiar with the term inverse, but we often use inverse operations when solving equations. For instance, if I have a number adding and I want to get rid of it, I subtract because addition and subtraction are inverse functions. Multiplication and division, also inverse functions. A square and a square root, inverse functions. They undo each other, or operations, I should say. So an inverse function is a function that undoes another function. If I plug in a value and take the output and plug it into the inverse, I get back to the original value that I plugged in. That's what an inverse function does. And so mathematically, how we describe this is using composition. So we learned about composite functions. This is one of the areas where we can use that idea of a composite. So first of all, notation is it looks kind of like an exponent. It's an f with an exponent, a -1 of x. So that would be read as the inverse of f of x once we've identified something to be an inverse function. And the rule or the mathematical property that we're going to check to prove that functions are inverses is we take the composition of f inverse composed with f and also f composed with f inverse. And for both of those compositions, if I simplify it, I should get x each time for every x in the domain of the functions. Okay, so that's how we're going to check to see if something is a function. There are a lot of properties that we should be aware of about inverse functions. For instance, a function has to be one-to-one in order for it to have an inverse. So that's always going to be the first thing we check if we're asked to find an inverse is it one-to-one? And we can use our horizontal line test on the graph of the function to determine this. So it's great to have a graphing technology like Desmos or graphing calculator handy when you're doing this, because the first thing you're going to want to do is look at the graph and do that horizontal line test on it to see if the function is one-to-one. If it's not, then we simply say it's not one-to-one, it doesn't have an inverse. Be careful with the notation on this. A -1 often means 1 over a value, but that is not how we're using this notation when we attach it to a function. So it's not 1 over f of x, it is f inverse. The domain of f is going to be the range of f inverse because they have this inverse relationship with each other. And the range of f is the domain of f inverse. Some other properties, if I look at the graph of f and its inverse function, they will be a reflection of each other about the line y equals x. So here's an example of what that might look like, where, I have the blue curve at the top here. This purple line is the line y equals x. And we get the inverse function is just a mirror image of that on the other side of y equals x. So this is another way to kind of look at inverses and see if you think they might be inverse functions based on their relationship on a rectangular coordinate system. And another way of looking at inverses is if you take any point AB from the function f, then the point BA will be on the graph of the inverse function and vice versa. So this just gives you some ideas of the relationships between a function and its inverse. Okay, so let's first see if we can verify that two functions are in fact inverses of each other. So here I have f of x equals x minus 10 over 3, and g of x equals 3x plus 10. And we want to figure out if these are inverse functions or not. Now, both of these are lines. They are linear functions, so they do pass the horizontal line test. So I know that they do have inverses. Now we just have to see if they're actually inverses of each other. So I'll start with a composition. So I'll do f composed with g. And then if I get x from composing those, then I will flip it and do g composed with f and see if I get x there as well. And if I do for both of them, then I can say that these are in fact inverse functions. If I get anything other than that, then they're not inverses. So just a reminder, when I'm composing, I'm taking the function closest to x in g composed with, or f composed with g of x, and I'm plugging it into the function f. So I'm going to start with the function f, and everywhere there's an x, I plug in the other function g of x. So it's the f of x was x minus 10 over 3, so the x gets replaced with 3x plus 10. And then I'm going to start simplifying this. So I can see I have 10 minus 10 in the numerator, so those will cancel out, and I end up with 3x over 3. And the 3's cancel as well, so I get just x. So this is looking good for these to be inverses of each other, but I do need to go and compose them in the other direction just to confirm that this is true. So g composed with f, now I'm reversing things. I start with the function g, and everywhere there's an x, I replace it with the function f. So 3 times x plus 10 becomes 3 times x minus 10 over 3, all plus 10. And here I can simplify this. The 3's will reduce, and I get x minus 10 plus the 10 at the end. And then those 10's cancel out as well, so I get x on that side as well. So when I composed it in both directions, I got x each time, which means that these are, in fact, inverse functions. Okay, so that's how I verify the functions are inverses, but we also need to be able to find an inverse function if I'm just given a particular function. So we can break this down into a 4-step process. Of course, I have to make sure that I'm dealing with the one-to-one function, or I don't even need to bother with this process. But if I have a one-to-one function, I'm going to take the function notation and just swap it out for a y to make it a little bit easier, nicer to work with. And then I'm going to go into the equation and I'm going to switch the x and the y, their positions in the equation, just swap them for each other. Then I will solve the equation for y, get that y all by itself on one side of the equation. And what I will have as a result of that will be the inverse function. So I'll switch it out to using the inverse function notation to replace the y once I've solved for y. Okay, so let's do an example with this. Find the inverse of f of x, and if it exists. So that if it exists is super important. I want to first make sure that I'm actually dealing with the function. Now this is a linear function, so I know it is going to pass the horizontal line test, but if you're ever unsure, go ahead and graph that in Desmos. So here, I can see here, I just have a linear equation. There's no horizontal line that I can draw through this that's going to hit the graph more than once. So this is a one-to-one function, which means I can go ahead and find its inverse now. So first step is replace that f of x with y. So now this is y equals 4x minus 7. And then I'm going to switch the places of the x and the y. So x equals 4y minus 7. And then I'm just going to solve this for y now that I've switched it. So I'll add 7 to both sides of the equation to get x plus 7 equals 4y. And then I'll divide by 4 to get the y by itself. So I have y equals x plus 7 over 4. And that is the inverse function. So I can replace the y with inverse notation there. So f inverse of x equals x plus 7 over 4. Now, if you're ever worried that you made a mistake with this, you can always verify it by composing f and f inverse, and you should get x when you do that. Okay, there's a couple examples below this video to help you practice this some more.